So today I'll be talking about uh, there is a stress block called as Whitney's stress block. This is one of the stress block that we often see in IS 456 while we design the cross section of the beam. So in this session I'll be trying to explain you in depth like how this stress block has came into picture, what's the exact philosophy of the way it has been shown in the codes. So just let's start with a basic cross section of just a normal beam. Let's assume this is a section having a width b, and let's say it is having an effective depth of around d from here to here. So often we see as the plane section remains plane before and after bending, so the strain which happens to be on the cross section comes out to be linear like this. So this is the strain which is coming in the concrete, this is the strain which is coming in the steel. So as we know, concrete collapses at a strain of 0.0035. This is the value which is coming from various experimental results that you can find in many of the uh, books as well as many of the codes. This is the general value that everybody takes for strain in concrete at collapse. So, strain in steel, as we know, sigma upon, that is stress upon strain, is always equal to your Young's modulus. So, if we want to calculate the strain, so how we will calculate that? Stress upon E. And as we know, the stress in the steel will be 0.87 Fy upon E. So this will be the strain which will be coming in steel. So if anybody has doubt how this 0.87 is coming, this is just the overall yield strength of steel after considering the partial safety factor of steel. So let's say Fy divided by 1.15. So 1.15 is the partial safety factor that you take for steel, and for concrete we take it as 1.5 as per the different codal provisions. As of now we are talking about IS 456, so everything I'm telling you with respect to that. So this is the strain which is coming in steel, but again there is a portion in steel which remains as a permanent deformation when it goes beyond its elastic limit. So that comes out to be 0.002. So the strain in steel comes out to be 0.002 plus 0.87 Fy upon ES. So I hope whatever I told you till now, it's pretty much clear to you. This is, I would say, this is the strain distribution across the depth of a particular beam that we are looking for. This is how it looks like. Now we will come at the stress block, the main part. So before jumping to that, what I'll do, I'll just try to explain you uh, from basics. Like let's say for concrete, if I try to draw a curve between stress and strain of a concrete, so the curve comes out to be parabolic like this. Okay, so this is your, I would say, the strength of concrete which we have got after testings. So let's say this is your FCK. So because of the uncertainties, there might be uh, reduction in the strength of the concrete. Let's say you have tested 100 cubes. So from those 100 cubes, you will not get exact strength of FCK for all the cubes. So in order to take that uncertainty into account, this curve we try to take only two-third portion of FCK into picture. Okay. After that, in that two-third of FCK also, after applying the partial safety factor into consideration, two-third of FCK divided by the gamma C, which is your partial safety factor of concrete. So if you calculate this all values, you'll come to know. Let's do it instantly. Two-third comes out to be your 6.6 0.67. If you divide it by 1.5, uh, if I divide it by 1.5, the value comes out to be 0.87, 0.67 divided by 1.5. Okay. So if you do this, this value will come out to be 0.45 FCK. So that's how this 0.45 FCK that you might have seen in many equations, this is how it comes like. So this was the essence of this overall, trying to explain you what I'm trying to explain you. This is how the 0.45 FCK comes into picture. So what I'll do now, whatever I have shown you in this picture, if you just rotate it, okay, just hold on to the concept and try to see what I want to say. So we know like this is the final value that we are looking at. This is the value which is of importance to us, this 0.45 FCK. So whenever you see the Whitney stress block, in that stress block, uh, this is your tensile force which comes out to be 0.87 Fy into AST, which is on the bottom portion. And I mean, this is just a concentrated force acting at the level where exactly your bars are. But now, if you just rotate this curve in this direction, so you will see this is how the curve comes out. And the value which is on the top is 0.45 FCK into B. Why B? Because I'm just multiplying the cross section with the strength. So this is how your 0.45 FCK into B comes out to be on top. And now, this is forming a lever arm. The centroid of this particular curve will be something here. Okay, just let me make it something like this. Yep. So now this will form a lever arm like this. So this lever arm will come to be as D minus 0.42 XU. Why 0.42 XU? Because this centroid of this particular block from the top will be 0.42 XU. That's why D minus 4.42 XU will be your lever arm. So now, as you know, what is moment? Moment is nothing but force multiplied by your lever arm. So what is the force? Force can either be in compressive force and it can either be tensile force. Let's assume it to be a compressive force as of now. So before that, before moving to that concept, let's calculate the force. How the force will come? Force will be nothing but the area of this particular stress block. Let me highlight this area. Let's say this is the overall area. If I calculate the area of this block, so as you know, stress multiplied by area will be your force. So as you know, 0.45 FCK is your stress in the particular stress block, the highest stress that you are getting, and it is moving parabolically. The area of parabola, you can assume it as two-third of whatever 0.45 FCK into B that you are getting multiplied by this particular portion. What is this particular portion? This particular portion will come out to be your XU. So this is XU. So when you will do two-third of 0.45, you'll come to know this is nothing but your 0.36 FCK into B into XU. This is the compressive force that is coming, and this is the exact equation which is given in the IS 456. And here we go, friends. This is how this value comes into picture. So, I mean, I'm explaining you everything from the scratch how these values are coming. So, if you like this video, please like, please subscribe my channel. It will motivate me to go in more and more depth and explain you more and more whatever knowledge I have with me, you know. So, yep, here as we go, you can see this is the value of compressive force that is coming. I have already explained how the value of tensile forces are coming. Now, coming back to the main Whitney stress block. So, as we have seen how this value comes, this is 0.45 FCK into B. Then this is the force that you are getting, with this 0.36 FCK into B into XU. This is your XU from the top. Then here at this level, please pardon me, please assume this particular force at the level of reinforcing steel. So this will come out to be 0.87 Fy into AST, and the lever arm will be D minus 0.42 XU. Now, coming back to the main picture, moment. The value of moment is equal to force multiplied by lever arm. Let's assume the force that we are taking is compressive as of now. So your overall uh, moment of resistance will come out to be something like this. And when will you use this equation? You'll use this equation when your XU, which is the let's say XU is the actual depth of neutral axis. This actual depth of neutral axis is coming out to be lesser than your XU limb. This is the limiting depth of neutral axis. This will come out when you will have a balanced section, and this is something which you are getting as of now for your section. And you will use this equation 0.87 Fy into AST D minus 0.42 XU. This equation you will use when you will have under reinforced section, when XU is greater than XU limb. And when you have balanced section, you can use any one of the equation because your section is balanced. The XU is equal to the XU limb. But please keep this in mind. We never go with over reinforced section because it doesn't give you the warning before the failure. That's why we always try to make a balanced section or either make it under reinforced. So, guys, this was the overall concept that many people try to understand how the equations are coming, how 0.45 is coming, how 0.36 is coming. I just wanted to explain this is how this overall expression is coming into picture. So if you just like this, whatever I have explained, please try to motivate me with your comments. And thanks a lot.